Hi all, and thanks for joining this webinar. My name is Christoph, and today we are going to talk about Speedgoat solutions to prototype power converter control designs and to test power converters and their controllers. I'm glad that we have Manuel Fedu on board, who will present most of the demos in this webinar. Also, we are thrilled to have Andreas Fixor from AVL present a hands-on demo leveraging the AVL Universal Inverter. So let's get started right away. Electric power converters impact a lot of aspects of modern life. More and more renewables need to be connected to the grids. So transmission systems are becoming even more vital components supporting the trend for power decarbonization and decentralization. Transmission system operators need to handle increasingly complex grids and meet new demands, because many electric loads need low loss and safe power supply. Here a study by the International Energy Agency. Ultimately, developing energy-efficient power electronics and smart control software is a winning move in a competitive business environment. So, in essence, power converters drive electrification throughout every industry. A key goal is to increase the overall efficiency of electric-powered systems while keeping the overall system cost low. Common challenges are to safely and reliably test precious power electronics hardware, and simulation testing using digital twins of high-frequency, high-power, and multi-domain systems can be cumbersome. To tackle these challenges, power converter development and testing solutions by MathWorks and Speedgoats are designed to assist you with technical and workflow challenges. So you can benefit from a fully Simulink integrated solution that provides flexible and automated workflows, powerful digital twin simulation software and hardware emulation solutions, and of course modular hardware-in-the-loop or HIL test systems that can scale with your needs. Before we dive deeper into testing workflows, let's look into the agenda of today's webinar. First, I'll introduce the solution's key capabilities and workflows. We will then shift the focus toward testing power converters, covering the four areas. First, rapid control prototyping, then power converter prototyping, then control hardware-in-the-loop testing, and last but not least, power hardware-in-the-loop testing. For each topic, our experts will present a hands-on demonstration featuring Simulink and Speedgoat test systems. Okay, let's start with the capabilities. Real-time testing can accelerate your development cycles without compromising safety, costs, or quality. You want to test safely without risking damaging precious electrical equipment or prototypes? Then, test as early as possible to reduce the time needed for iteration loops and thereby your time to market. And improve your knowledge of the system to ensure its compliance with new requirements and their regulations. Engineers increasingly rely on model-based engineering to address apparent challenges while keeping the pace of innovation. They use digital twins to develop agile and safe power electronics control systems and test them. Yet, transitioning seamlessly from early requirements and integration testing remains challenging. What's needed is to stay within a single environment and automate testing end-to-end. Speedgoats and MathWorks power converter control design and testing solution will assist you in this journey. So let's look at a typical power converter control development process. We will use this visual throughout the entire webinar. So before your power electronics converter and load is in operation, you typically start with modeling and simulation on the desktop. This is shown on the left in this graph. On the other side, a final step before commissioning your power converter is probably testing the system at full power with emulated loads, here shown on the very right. We will make sure to cover all intermediate test and design steps throughout this webinar. Suppose you want to test an embedded controller of a novel power converter. You do that by staying in Simulink without having to learn additional tools. You configure your model for real-time execution, select the appropriate HIL simulator, and deploy your application to run on hardware directly from Simulink. Simulink blocks represent any I/O and protocols. Placing them in your model and configuring them is very simple. I/O support includes automotive protocols, fast analog and digital I/O, as well as emulating plant and fault insertion hardware. With over 200 I/O modules available, we ensure your workflows remain uninterrupted. Documentation and examples are accessible with a few clicks, integrated into the MATLAB documentation. Switching back and forth between desktop and real-time simulation is also very simple. For instance, we used system variants to switch between different testing scenarios quickly. Simulink isn't only your deployment environment, but also your hub for real-time testing using the same logging and instrumentation capabilities you were already using during desktop simulation. You can also open access to your real-time applications for non-Simulink users with tailored MATLAB apps. You can pack these as desktop apps or web apps that you share royalty-free with your test engineers. Simulink and MATLAB apps are great for interactive testing, but to reliably test your ECUs, you will need to automate testing. Considering these needs, the solution seamlessly integrates with MATLAB, Simulink Test, and third-party automation or continuous integration tools. Let's have a closer look. Because Simulink and MATLAB are so closely connected, you can quickly script actions, deploy and control hill tests from MATLAB. As demonstrated here, you can also interface your hill system with external programming environments like Python. So, suppose your team is using a different programming language. In that case, you can spend more time automating your testing and less time recoding in MATLAB. Scripting tests can be of great help, but for rigorous testing, you'll need a test automation suite that enables true end-to-end automation. Simulink Test is a great building block within the MathWorks ecosystem that can help you with this. It lets you create and manage test cases, perform requirements-based testing, and quickly create hill test campaigns for existing desktop simulation test artifacts. The assertion of results is fast and easy using inbuilt visualization tools, and you can automatically generate test reports and share them with stakeholders. You can also integrate with the third-party test automation tools using the ASM-XIL API. So this lets you flexibly build your hill system, reuse test campaigns, and available in-house know-how. You can further automate and boost the productivity of your testing using continuous integration. For instance, you can use source control within your projects, quickly track, compare, and qualify changes, and integrate CI platforms like Jenkins, GitHub, or Azure DevOps to orchestrate testing and have hill systems operating around the clock. Let's now have a closer look into the hardware and integration benefits, starting with the hill simulator, which is a core component of your test system. The mainstay for hill testing is the performance machine. It's the most scalable and performant system. It is suited for desktop use, but also for rack mounting. The mobile, baseline, and unit machines are smaller and rugged, making them better fit in hill applications requiring more portability and fewer I/O channels. Speedgoat target computers come with multi-core processors supporting concurrent execution and co-simulation with FPGAs. They also have extensive onboard connectivity, including several Ethernet-based protocols, serial, and video interfaces. The PCI Express serial interface is the backbone for I/O connectivity, enabling the lowest latencies, fast analog sampling, and high-speed I/O. You can update and scale your system anytime with I/O expansion units or by implementing distributed simulation architectures. Implementing a hill system can be complex and time-consuming. But it doesn't have to. We provide you with all the specific expertise so that you can focus on your core task, the testing and validation of ECUs. With the help of our project management and production teams, we can provide you with the fully customized rack systems, including rack-mounted hill simulators and easy access to all signals via breakout and I/O panels. We will integrate power supplies, actuators, inverters, and any kind of power electronics, as well as project-specific PCBs for signal routing and conditioning. For prototyping converter control designs or for testing converter and their controllers, you need to connect your test system to your power electronics hardware. To do so, you can leverage Speedgoat's fast signal level I/Os. thereby benefit from high bandwidth analog interfaces and nanosecond resolution digital I/O for PWM generation and capture, resolver, quadrature encoder, or SPI. Besides that, power electronic systems also involve communication interfaces with other control layers, exchanging information about set points and system status, for example. For this, Speedgoat I/O modules support most industrial communication protocols for buses and networks such as CAN, Modbus, and many more. Now, I'm going to hand over to Manuel for the demos about rapid control prototyping.
Thank you, Christoph. You nicely covered some aspects that streamline testing. So now let's cover some workflows for power electronics using real-time testing. Let's go to our overview visual. After validating your system design with desktop simulation, you can transition to control design prototyping, which is often referred to as rapid control prototyping, or RCP in short. At some point, you need to prove that your control design works well in real-world dynamics using the real power converter and motor or load. When doing this, you will need to iterate on your designs, tweak parameters, and continuously monitor real-time performance. For this, you benefit from the close Simulink integration. It allows you to navigate seamlessly between control design testing and fine-tuning your algorithms. Let's look at rapid control prototyping setup in action. In this demonstration, I'll use a model where we run our controller in real time and drive the real inverter and electric motor through the I/O interfaces. For rapid controls prototyping, we use a Speedgoat configurable I/O module, which is configured to enable PWM generation, quadrature decoding, and analog and digital signals. This setup enables to spin the motor and assess the system response to the controls. For example, we want to change some control parameters and directly observe the changes in control performance. Here, the feed-oriented controller runs PID control for the velocity control loop. At this point, you may already have a reasonable estimate for the controller gains through testing against desktop simulation. Now it is time to verify and fine-tune the control parameters against the real inverter and motor. Note that many parameters, such as the proportional and integral gains here, can be adjusted even during runtime of the real-time application, and changes don't require a rebuild of the model. I've started the model again, and you can see the motor and the lab data from the simulation data inspector. I've added some dashboard controls as well to quickly change the speed command directly from the Simulink canvas, which allows me to see the effects of variations in the controller gains. Depending on your application, you might need to update multiple parameters simultaneously to test a desired effect. We activate batch mode on the real-time tab, and then we can adjust all the parameters we need. The changes will only be uploaded to the target machine once we click Update all parameters. To switch back to normal mode, simply click Batch mode again to deactivate it. MATLAB and Simulink also offer you different tools for PID tuning and automatically find optimal control gains to achieve a desired response. Now let's explore power converter prototyping that enables to leverage off-the-shelf power converter for rapid prototyping. Maybe at a given development stage, you need to test power electronics controls without having the final converter available. But you still want to find the best control strategy to prototype your converter design and to test the electric load with real power flows. This is where using a rapid converter prototyping setup can help. One example is the AVL and Speedgoat test system for motor inverter prototyping. You can leverage AVL universal inverter to drive your electric motor. The controls can be deployed to a Speedgoat real-time target machine interfacing with the inverter via fiber optic communication. And now I'm handing over to Andreas Fixer from AVL for a hands-on workflow demo.
Thank you, Manuel. In the next few minutes, I will explain how to use the AVL Universal Inverter together with the Speedcode real-time system to split the controller software from both devices for rapid prototyping. Let's have a look at the typical setup. In our case, the unit under test is an electrical motor, or more precisely a permanent magnet synchronous motor, or PMSM for short. Of course, it could be any other type of motor. The motor is connected to the AVL Universal Inverter, which is equipped with a control unit, the black box at the top of the inverter. Please don't confuse this with the Speedcode real-time system that comes next. The control unit has a predefined set of motor control algorithms that can be used to validate the electric motor each time. The behavior of the control software is modified via parameters or lookup tables. In some cases, changing the parameters is not enough, especially in the case of rapid prototyping, where you want to find out how your own control idea works. To do this, we implemented the Aurora interface for a fast connection to Speedcode. You can either use predefined examples from the Simulink library or create and use your own software. We have implemented a layer concept to clearly separate which software runs where. Layer 0 is protected by AVL and more or less contains the PWM. Layer 1 can be switched off in Spectra, and the software functionality, the transformation, field-oriented control, and duty cycle can be moved to Speedcode. In this case, the Spectra control unit requests the duty cycle as an input. Turning off layer 1 will automatically turn off layer 2. Layer 2 can be switched off independently of layer 1. In this case, only the controller in Spectra is switched off and can be moved to Speedcode. This flexible layer concept helps us to try out your own ideas quickly in a structured way. Here's an example of a motor control software that runs entirely on Spectra. Simple said, all the functionality is in Spectra. Now let us see if we switch off the layer 1 and 2 functionality in Spectra and let Speedcode take over layer 1 and layer 2. In this case, as already said, Spectra is waiting for a duty cycle as an input. In case you just want to test your own controller, we have implemented layer 2. This simply switches off the controllers in Spectra and allows you to use your own custom controller on Speedcode, but the rest of the software stays as it is. Before we show you how we use it in our testbed, a brief explanation of the use case. In the demo we will show you how we move the speed controller from Spectra to Speedcode. To do this, we provide an interface block in Simulink that allows you to easily connect your own speed controller. Now we will show you how to connect to Speedcode real-time system, modify the software in Simulink and upload it to Speedcode. In this case, we connect the Universal Inverter to Speedcode via an optical interface. Next, we connect Speedcode to our application PC to be able to upload the speed controller later. We are now ready to implement the new speed controller by using Simulink. Now I select the speed controller from the library, but you can also create your own. Then we need to compile the controller. Finally, you can set the speed values using the graphical interface. In our case, we will do 3 steps: 1000, 3000 and 6000 RPM. Now I am going to hand over to Manuel again.
Many thanks, Andreas. Leveraging off-the-shelf converters is greatly speeding up the process of testing power electronic concepts. Now let's see how developers leverage controller hill testing to validate the controllers. We are looking at our development overview again. At some point in development, you'll need to test the embedded controller. Also there, Simulink and SpeedGoat can be of great help. For controller hill testing, you connect the inverter controller to a test system running a digital twin of the power electronics system. This enables you to be less dependent on hardware and expensive labs, leading to faster development cycles and cost savings. You can safely assess injection of faults and disturbance and achieve high test coverage and standard compliance through systematic and automated testing. Let's see how you can build such a system using SpeedGoat and MathWorks hill test solutions. First, you need to run a real-time simulation of the power electronics system. Simulation fidelity and speed are crucial for converter hill simulation, so we offer a twofold solution to meet a varied set of requirements. For simulating average inverter models that ignore switching effects and for detailed switching models of converters running up to 10 kHz, you can use a CPU-based workflow. This combines multi-core processors, high-speed configurable I/O modules, and C-code generation capabilities of Simulink and SEMScape Electrical. Then, to accurately simulate the fast switching dynamics of high-frequency converters, you can use a SpeedGoat programmable FPGA to increase hill simulation bandwidth to a megahertz range. Let's look closer at these solutions, beginning with a CPU-based solution. You can start by creating your power grid and power converter model using SpeedGoat reference examples. Simulink and SEMScape Electrical built-in libraries provide easy-to-use blocks, including various power converter topologies and electrical machines, so you can easily customize the examples to your needs. Tuning the fidelity of the converter and electrical components is easy. For instance, you decide whether the inverter should work as an switched or average inverter. Finally, you configure the model with various controller interfaces, including Simulink blocks that emulates power system phase currents, capture of PWM signals with nanosecond resolution, and interface with power grid networks. You can change the I/O functionalities of the configurable I/O from Simulink at any time without the need to swap the hardware. Let's check the FPGA workflow. You can start with fully assembled hill examples and FPGA-ready templates covering the most common inverter topologies. You modify these to integrate your own testing requirements. For instance, you can adapt connectivity with controller hardware or modify elements within the topology, all using the same drag-and-drop Simulink experience we've seen before. As for the CPU workflow, you can run your FPGA model in desktop simulation and iteratively validate your design. To generate an FPGA application, you call Simulink HDL workflow, which assists you with the FPGA intricacies like generating target-optimized HDL code and mapping interfaces. The resulting FPGA topology is represented with a Simulink block, so you can easily interface this with your additional system-level components and benefit from MATLAB and Simulink logging capabilities, now with a nanosecond resolution. On the hardware side, and depending on your application requirements, you decide to either include a high-speed configurable I/O or a programmable FPGA. You can extend the setup with I/O interfaces and communication protocols like CAN, Modbus TCP, and BMP3. The wall can be stacked in a rack to integrate power stages, signal conditioning, temperature emulation, fault insertion, and breakout panels that facilitate measurements and connectivity with your controller hardware. Let's now illustrate these workflows with two demos, an NPC solar inverter demo for the CPU workflow and a dual-active bridge converter for the FPGA workflow. You can download the demo files in the SpeedGoat Knowledge Center. Let's now explore a solar inverter hill setup in action, outlining the CPU workflow with configurable I/O modules. The hardware setup for this demo consists of a development computer enabling instrumentation and real-time testing, a performance real-time target machine running hill simulation of a grid-connected solar PV system, including an NPC inverter. The device under test is a microcontroller running the inverter controller and MPPT algorithm, as well as an oscilloscope to monitor the voltage and current of the grid and DC bus of the simulated power system. Let's now switch to Simulink and check our HEAL system model. The model is structured around two primary blocks: an instrument panel modeled using Simulink dashboard components to enable real-time interactive testing directly from the Simulink canvas, and the power electronics model, which includes the interface with the inverter controller. The electrical system consists of a 25 kV microgrid connected to a 400 kW solar PV system. It is implemented using the Simscape Electrical Specialized Power Systems library. The grid inverter is a 3-phase, 3-level NPC switching inverter directly controlled by PWM firing pulses generated by the inverter controller. Hardware interfaces between the simulated power system and the inverter controller are established using a PWM interface that captures the controller gate switching signals. Additionally, there is a digital to analog interface that outputs the simulated voltages and currents for the power grid and DC bus. These interfaces are enabled through a configurable I/O module configured to use direct memory access, which reduces overall I/O latency and let us run this application at 40 kHz. Let's kick off our HEAL demo to see how different weather conditions affect the MPTT controller. Here, the predefined weather conditions simulate a typical day from morning to late afternoon, with temperature and irradiance levels rising and then falling. We're condensing this input profile on a 60-second time window for illustrative purposes. The controller algorithm has been deployed to the microcontroller on a test. We switch to the HEAL model and run the application in real time. Now the simulation is operating in a closed loop. As the irradiance increases, the solar panel produces more power. The MPPT algorithm continuously tracks the DC bus voltage and the solar panel output, adjusting the DC bus voltage to optimize power output under varying conditions of temperature and irradiance. While the application runs, we can also monitor the control PWM signals issued by the inverter controller with an oscilloscope, or use the simulation data inspector to review additional model data, like the captured PWM duty cycles and the force phase voltage waveforms of the NPC inverter. In addition to the predefined weather profile, you have the option to manually adjust the irradiance and temperature. Let's imagine that a thunderstorm hits in the middle of the day, causing a sudden drop in both irradiance and temperature. We see an immediate change in power output from the solar panels, as well as shifts in the DC bus voltage and current. Next, we'll assess how changes in grid frequency impact the overall stability of the power system. Using the instrument panel, we set a 5 Hz frequency variation to occur at 20 seconds, returning to the nominal frequency of 50 Hz after 1 second. During this test, you might notice a minor disturbance in voltage and power when the frequency changes. However, the solar system remains synchronized with the grid frequency. For our final test, let's simulate a phase short-circuit fault and assess system robustness. To initiate a fault, simply flip the fault switch to the on position. This action will create a 3-phase short-circuit fault on the grid side. Let's stop the simulation and check acquired power system data in Simulation Data Inspector. You'll notice the fault lasted only about 1 millisecond. During the fault, the inverter and AC waveforms distort, showing noticeable spikes in bus voltage and current, which is expected. Despite these disturbances, the system recovers quickly once the fault is cleared. Now let's look at a demo of a dual-active bridge, or DAB for short, converter controller HEAL testing, outlining the FPGA workflow. This test system is equipped with a Simulink programmable FPGA, enabling super-fast power electronics simulation and controller connectivity. The device under test is a microcontroller running the DAB converter controller. A dual-active bridge is a DC-DC converter that provides bidirectional power flow and galvanic isolation. A dual-active bridge is constructed from 2 full bridges that are separated by a high-frequency transformer and inductor. Designing a DAB requires a combination of digital control design and high-quality electrical simulation. Here is the SpeedGoat dual-active bridge converter controller hill reference example system. This example showcases hardware-in-the-loop testing of a DAB converter microcontroller. First, you can run model-in-the-loop desktop simulation of both the DAB converter and controller on your development computer. This simulation uses Simscape Electrical to model the converter. You can use this variant as a golden reference design to validate the subsequent design stages. So, let's run this model and save the simulation data for later use. Now, to test controllers switching at several hundreds of kilohertz, like DAB used in electric vehicle onboard chargers, we need a design suitable for fast real-time simulation. This involves using simulation time steps in the nanosecond range and high-speed digital and analog connectivity. This can be achieved with SpeedGoat Simulink programmable FPGAs, utilizing Simulink and Simscape HDL code generation capabilities. You can shortcut this path using our FPGA power converter example models, which cover established power electronics topologies, including DAB or PFC. These examples are included in the SpeedGoat motion control I/O block set and are fully optimized for SpeedGoat Simulink programmable FPGAs. With simulation time steps of just a few nanoseconds, these designs are perfect for testing converters operating at very high switching frequencies. The example features a DAB converter topology, implements the switching logic of two full bridges combined through an inductor tank. This design uses a fixed point implementation to ensure optimal execution latency and resource usage on the FPGA. To generate an FPGA application, you use the Simulink HDL workflow using its interactive interface. This tool helps you navigate FPGA complexities like generating target-optimized HDL code and mapping the various FPGA interfaces. Your DAB converter design is now encapsulated in a Simulink library block, ready to be integrated into your system-level model and be run in real time. Note that you can combine the FPGA-based nanosecond resolution simulation with CPU-based simulation for slower dynamics, such as battery electrical and thermal behavior while charging. To verify the correctness and proper development of the FPGA design, you can run a simulation using the real-time model-in-the-loop mode. This mode allows you to simulate both the power converter and controller in real time, with the converter simulation accelerated on the Simulink programmable FPGA. Let's proceed by running the simulation and then compare data with our golden reference baseline. Note that some differences are expected between the two designs. The desktop simulation model employs detailed MOSFET models, while the real-time model uses a switched linear fixed-point mathematical model for the DAB's full bridges. You can also use this simulation mode to observe voltage and current switching dynamics with a logging resolution of 8 MHz here. It's now time to prepare the Hill controller setup. We connect the microcontroller to the Hill test system using appropriate cable and PCB. Here we are using SpeedGoat Launchpad Development Kit, which streamlines interfaces between controller and the Simulink programmable FPGA. We switch to the Hill system model and select the Hill simulation mode, build and run the application real time. Now the simulation is operating in a closed loop. We can test the controller under various loads. We can ensure the bidirectional power flow enabled by the dual-active bridge at various currents, with a charger battery or provide power to the grid. Also, we can trigger various faults in the DAB switches and assess how they impact the system and the controller response. Here is the hardware setup in action. You can see the inductor current waveforms and the DC current on the oscilloscope. This wraps up the controller hardware-in-the-loop testing demo. Now, before deploying a new power converter, it needs to be tested in a safe environment at actual power levels. This is where power hill testing comes into play. On the overview visual, we are now in the final stage of testing before deploying the solution. We'll be testing the power converter at actual power levels, referred to as power hardware-in-the-loop testing or PHIL testing in short. Let's now have a look at an overview about PHIL hardware and the final demo of today's webinar. Power hardware-in-the-loop testing is the last step before connecting the power converter to the rest of the system. It is also the last option to test safely critical aspects of the controller or simply test a new power electronics prototype in real conditions. Indeed, during PowerHIL testing using the amplifiers, the same current will flow in the inverter as when it is connected to a real load, such as an electric motor. Traditionally, you would require a motorized test bench to apply mechanical loads and to measure torque as well as speed. This type of equipment is expensive, and preparing a specific test can take hours or even days. In this demo, we'll show you to test key functions of your motor drive, such as testing the overcurrent protection and setting up automated tests with predefined load profiles. For power hardware-in-the-loop testing with large current and voltages, we integrate all components into a rack to benefit from additional safety. Here, the motor drive consists of a 3-phase 2-level inverter that is controlled by a compact speedcode target computer that runs the controller algorithm. The PMSM motor model runs on the performance real-time target machine, where its FPGA calculates the motor currents depending on the voltage coming from the inverter. The currents will then be generated by controlling the 3 power amplifiers, which are directly connected to the output of the inverter. Last, we have installed current probes to measure the current flowing from the power amplifier on an oscilloscope. The electrical connections are wired in the back of the rack to allow clean and safe integration and prevent accidental manipulation. The wiring represents the motor topology. We decided to test a delta configuration that creates higher inverter line currents at lower motor phase currents and is more demanding for the inverter. Inductances are added to allow the power amplifiers to correctly emulate a motor submitted to switching events. To recap, in our PowerHIL demo, we test a motor drive consisting of a field-oriented motor controller and a 3-phase inverter, using a power hardware-in-the-loop test system where a motor model controls 3 current sources. We will test the motor drive against motor controller inputs like the speed set points and the PWM frequency. And we will also be able to change the plant operating conditions by applying a simulated load torque to the motor or introduce resistance fluctuations. Let's have a look at the models. To run the PMSM motor on the FPGA, we have prepared the source model where the inputs and outputs are configured. The phase voltages, which are acquired by dedicated sensors, are fed to the model through the analog inputs of the I/O module. The motor model will calculate the motor currents to emulate, and the position feedback will be sent using the quadrature encoder function to digital outputs. They will be wired to the controller, while the currents will be connected to the analog inputs of the 4-quadrant power amplifiers. Last, we have also configured digital outputs to enable the power amplifiers directly from Simulink. The main model contains a user interface to control the power amplifiers and to modify the conditions of the simulation, like the external load and the motor internal electric resistance. The controller model is the standard FOC using encoder and electric current feedback. We have added a management layer for the overcurrent faults that we want to test specifically in this demo. Before starting the power hardware-in-the-loop simulation, we make sure that safety is guaranteed. We first run the simulation on the plant real-time target machine and turn on the amplifiers. From now on, the PowerHIL test system is emulating the motor. We enable the inverter which will now react on the PWM input from the controller. You can see that the motor starts to turn and follow the speed command. We reduce the PWM frequency to 1 kHz to observe the current ripples on the oscilloscope. Compared to standard controller hill testing, we are now reading real currents of a few amperes directly from probes integrated in the power hill rack. Let us now experiment with the external conditions of the motor. Unlike with a physical test bench, we only need a few seconds to make drastic changes to both the controller and the motor in a completely safe environment. We first increase the load on the motor and see that the controller reacts by injecting higher currents. We see that we reached our overcurrent limit of 9 amperes at roughly 20 cm². This is a good indication that our software protection works properly. Let's check the behavior of the controller and inverter when increasing the resistance of the motor. This could be due to an increase in ambient temperature or from a failure of the cooling system. In closed loop, the controller recovers without a fault. However, switching to open loop triggers a large current spike and a fault is detected. One last interesting test is to increase the resistance alone in open loop. As the resistance increases, less current can flow in the coils, and the torque produced by the motor gradually decreases up to the point where the load will make the motor spin backwards out of control. Interestingly, the resulting back EMF currents did not trigger any faults. These types of scenarios with the motor spinning out of control while connected to a real inverter are very valuable safety tests, but extremely hard to set up experimentally because of all the risk involved due when mechanical parts take high rotating speeds. Motor emulation is a huge benefit for such cases. Now, to be more consistent, we want to automate such tests and run specific scenarios on demand. To do that, you can use the signal editor to create scenarios and use Simulink Test to manage them. The signal editor can be a simple input of the model, and here we set up a load profile like we would do with a controllable load on a real motor test bench. We then set up a Simulink test with a reference speed profile that will have to be matched with a certain tolerance, and simply run the test from a script or from the test manager. The test will activate the scenario and apply the load profile on the motor. We see how the controller needs to cope with the load changes in real time, or simply look at the result once the test has ended. Here the test has passed because the speed outputs matches the previously simulated profile within the tolerance. Let us recap what we have seen in this demo. We were able to verify the inverter design and performance by reproducing the behavior of the motor at the leads of our inverter and mimic full power operating conditions. We changed the switching frequency and observed the real current ripples and could confirm the synchronization and balancing of the 3 branches. We experimented with the load torque and resistance variations to verify the conditions for overcurrent fault detections. At last, we implemented a load profile to allow consistent test automation and automated testing. You can leverage our PowerHill solutions for various power levels, from 1 kW with the SpeedGoat PowerHill testbed that we just covered, to hundreds of kilowatts, for example with the AVL eMotor emulator. For high power motor emulation, SpeedGoat can interface to AVL eMotor emulator. This emulator uses Aurora communication protocol with a low latency interface in the 1 to 2 microsecond range. For this, SpeedGoat provides a proven Aurora interface to connect the AVL eMotor emulator. Therefore, you can use a motor inverter testing solution as follows. You stay in your MATLAB Simulink development environment for plan modeling and test case description. You run the plan model on the Speedcode test system and use an FPGA I/O module running Aurora communication to interface the AVL eMotor testbed. The AVL eMotor testbed provides a motor emulator and a battery emulator that enables to test motor drives at full power. Let's see a short video of this setup in action with the Speedcode test system running a virtual vehicle model. The unit on the test is a motor inverter tested with real power using the AVL eMotor emulator testbed. And now I'm handing over again to Christoph to conclude this webinar.
Thank you, Manuel. These were very powerful demos that nicely outlined the testing workflow. I hope each of you obtained some tangible outcomes from the demonstrations, and let's together now look into the key takeaways from today's session. So there's a single key takeaway for you today. Speedcode Test Systems and Simulink provide a testing solution for all aspects of designing and testing power electronics controls. Why is that? Well, first, you can model and simulate digital twins of your power converters, including ultra-fast switching dynamics in real time. Second, you can develop and test in a single, fully integrated environment that fosters agile development and automated testing. And finally, Speedcode test systems are performant, modular, and scalable. They allow you to prototype control designs, perform hill tests with a controller, and test drives at full power. Thank you for staying till the end of this demo-packed webinar. You want to learn more about real-time controls testing? Then find additional content linked here.